These are your 12-6B notes on periodic functions. We are going to see what the parent function of a sine curve looks like. We're going to see what the parent function of a cosine curve looks like. And we are going to actually adjust the parent functions. We're going to stretch and compress the graphs both vertically and horizontally. So they're like the dilations of these functions. So we're going to start graphing these things. It's not as bad as it sounds. Lots of symmetry is used, lots of patterns. So it's a lot easier than even graphing a parabola. So what we're going to do, first of all, is we're going to look at the sine values in relationship to the degrees and the cosine of each degree on that unit circle. So for the first one, we are going to graph on the coordinate plane y equals the sine of theta, and theta is the angle. So if I plug in an angle and take the sine of it, we're going to graph that on a coordinate plane. So the first thing I want to point out is that our coordinate plane now is stretched horizontally. So these are actually really easy to graph using line paper rather than graph paper, because we're going to use a lot of the horizontal lines. So if you use the line paper lines, it'll help you organize your work much better than graph paper. And then the other thing I want to point out is scaling is so important. Labeling your increments is so important here. And that's where the symmetry makes this so easy. As long as you label it, you can scale your size, your coordinate plane to any size that you want. So where I'm going to get these values from is the actual circle, unit circle that we filled in before. Now, these ordered pairs represent the cosine of theta and the sine of theta. So if you remember from before the weekend, this was our homework. And so the sine of theta is the second value going all the way around this unit circle. So actually, I'm going to go ahead and I'm going to highlight all those values. So the sine of 0 degrees is 0. The sine of 30 degrees is a half. 45 is the square root of 2 over 2. And 60 is the square root of 3 over 2. 90 tops out at 1. After 1, we start going back down around the circle. So we hit that root 3 over 2, root 2 over 2, a half again, back down to 0. And then we start getting into some negative sine values. So I'm just going to highlight all of these in blue. You don't have to do this. You don't actually have this graphic. But that's what we're going to graph. So we're going to kind of unravel this circle on the coordinate plane. Now, a couple things. Okay, a half is just going to be 0.5 on that coordinate plane. I'm not going to actually graph 45. I can point it out, but I want to scale my increments evenly. So instead of going 30, then 45, I'm going to count by 30s each time. But 45 will get hit. You'll see that 45 reaches 0.7. And 0.7 is just the square root of 2 over 2 in a decimal format. And then 60 degrees will give us approximately 0.86. So we do top out at 1. That is the highest value this goes on the unit circle because it's a unit, can't go beyond the radius. And the lowest point is -1. So when I go back to the other screen, I'm actually going to split my screen here. And I want to see both of these values. So when I go around, I want to label my scale in 30-degree increments. So 30 degrees here, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, and 360. So I didn't put the 45s on there, but they're halfway between 30 and 60, so I can talk about them. My vertical scale, I top out at 1, and I bottom out at -1. Now, because we go horizontally so far, I want to make sure that I'm still going up to 1 and going down to -1 when I get all the way over to 360. So we're going to make a nice light dotted line going across horizontally, just as a guideline. So that kind of guides us where 1 is. So in reference, as we're trying to put these decimals on there, we know where 1 is. And then I'm going to do the same thing for -1. Now, I know -1 looks closer. It's just a visual, you know, it's misleading because of the scale. all those degrees are making it look a little closer, but they are the same distance apart. The other thing we can do is we can also talk about the negative degrees. So this would be negative 30 and this would be negative 60 here. Okay, so I'm going to take all of those blue sine values and actually graph them on this coordinate plane. For 0 degrees, I'm at 0. The sine of 0 degrees is 0. So my sine curve starts there. When I move to 30 degrees, I'm at 0.5. So just roughly halfway between. I'm going to skip over the 45. I'm going to go to 60. So 60 degrees is 0.86, so almost 1. And 90 hits 1. So that's the first quadrant. It was positive because all of them are positive in the first quadrant. Now I'm heading into the second quadrant. 120 is a positive 0.86. 150 is a positive 0.5. And 180 is 0. So if you look at that peak right there, it's symmetrical. I approached 1, going from 0.5 to 0.86, and then I left 1 and approached 0 again in the same values, 0.86 and 0.5. So it's that symmetry that we're going to use to graph these over and over again. Now using CAST, all students take calculus. In that second quadrant, my sine values were still positive. Now if you look when we approach the third and fourth quadrants, I'm going to go below the x-axis, and that's when your sine values are negative. So for 210 degrees, I'm at a negative 0.5. For 240, I'm at negative 0.86. And 270, I bottom out at negative 1. At 300, I'm still negative, but I'm at negative 0.86. I'm working my way back up. 330, I'm at negative 0.5, and 360, I'm at 0. Now, if I continued into 390 and 420 and every 30 degrees, it would just repeat this process. And so here's your first, this is your parent function of the sine curve. It does continue in both directions, on and on. Even if I went to negative 30 would be the same thing that positive 330 was, because they're in the same spot. And so there is your sine curve, but it goes on and on forever, peaks and valleys all the way throughout. So something I want to make certain, when you graph the sine curve, I'm looking for basically 5 points. So if you want to put this off to the side somewhere, okay, you don't need a table of values, but if that's your x-axis, what I'm looking for your 5 points is that your sine curve starts at 0, it ends at 0, and it's in the middle at 0. It peaks and it valleys in between those. So there's your 5 points. And when you do those 5 points, those key 5 points, and you connect them in a curve, you look at it and it sort of makes a sideways S. So I always think of a sideways S, you're going to see a peak and then a valley for the parent function of the sine curve. So now what we're going to do is the same concept, but we're going to take the cosine curve. And so if I do the cosine curve, if I highlight all my cosines, when I start at 0, we're up at 1. So that's a little bit different. 0 degrees, we're going to start up at 1. Then we go down to 0.86, down to 0.5, down to 0. Then we go below the x-axis because in the second quadrant, cosine is negative. And we go down to negative 1. Third quadrant, we're still negative, but we're approaching the x-axis now, going up to 0. And then the fourth quadrant will be above again, and we're going to end up at 1. So let's go ahead and put the scale, again, by 30s. So just quickly scale your x-axis in degrees. And then, again, we peak at 1, and we bottom out at negative 1. We're going to go ahead and put our guidelines in there again, just like the sine curve. And we can graph this. I'm going to put the negative 30 and the negative 60 on there as well. All right, so to start at 0 degrees, what we're actually graphing this time is y is equal to the cosine of theta. So the cosine of theta, if theta is 0 degrees, the cosine is 1. So we're going to start up here at 1. The cosine of 30 is 0.86. The cosine of 60 is 0.5, and the cosine of 90 is 0. Now we're going to hit the negatives. We're in quadrant 2. 120 is going to give me negative a half. 150 is going to give me negative 0.86. And 180 is going to bottom out at negative 1. We're going to work our way back up to 0, but we're still negative. At 210, we're at negative 0.86. 240, negative 0.5. And 270, we're back up at 0. And then we're going to go into the positive when we reach quadrant 4. 0.5, 0.86, and then 1. So the same values that we used in sine are used in cosine. They're just in different spots. But we still bottomed out at negative 1, topped out at 1. And when you connect this, it looks slightly different. So rather than a peak and a valley here, what you really see is one great big valley and two partial peaks. If you were to continue into the negatives, you'd see the rest of that peak over here. And if you continue beyond 360, you'd see the rest of the peak there. So you're looking at one great big valley and half of two peaks. So what I like to mention when we graph cosine, I like to keep it simple. If this is your horizontal axis, 5 points, cosine starts up, it ends up, and to balance the two ups, we need one down. So in the middle, we're down. 2 ups, 1 down, and then halfway between, we're at 0 in each of those cases. So it's a great big peak, and I like to think of it, it's a stretch, but it helps. It looks like a C. It looks like a sideways C. So the sine curve looks like an S, and the cosine curve looks kind of like a C. So those are the 5 points that we're going to graph each time. We're going to go into next is the vocab for these dilations. We're going to stretch and compress this graph. So these are your parent functions. A lot of things in the world mimic these curves. If you guys worked with sine waves at all in physics, they mimic the sine curve. And it doesn't always fit the parent, so sometimes you have to squish the parent in or stretch it horizontally or vertically. And so that deals with the period and the amplitude of the graph. So a little bit of vocab there. So the first thing we're going to discuss is the period of a function. A periodic function is a function that repeats over and over and over again. The period is the least positive value for which a graph repeats. So it has to be a positive number. Periods cannot be negative. And the sine and cosine waves are periodic functions. In other words, if we keep going around the unit circle over and over again, you're just going to see the peaks and valleys over and over and over again. And so the period of the sine and cosine curves is 360 degrees or 2 pi radians, depending on how you want to look at it. After 360 degrees, it would repeat. All those values repeat. Anything less than 360, you haven't quite peaked and valleyed enough. So there's other types of periodic functions. These don't have actual names, but they repeat. And so the repeat is so when you look for the period, I like to start at 0. You're looking for the horizontal distance the graph travels before it repeats, horizontal. So if I start here, I'm starting at 0. Okay, so that's the horizontal measurement. If you start at 0, the period's a lot easier to calculate. So as I trace my graph goes up to 1, goes back down to -2, goes up to -1, and goes back down to -2. That's one period of this function. If I were to trace again, I'd already gone up to 1, so that would be a repeat. So if you look at the distance traveled horizontally between 0 and 4, the period of this function would be 4 units. Now you don't have to start at 0. If I, for some reason, want to start at 5 up here, and I looked at this W-shaped part of the graph, that went from 5 all the way to 9, and when you subtract and figure out the distance between those two, you end up getting 4 again. So the easiest place to start is 0, but you don't have to start at 0. If you look at the example in part B here, for part B, if I start at 0, I'm up at 2, I go down, and I'm back up at 2. So the period of this function would also be 4. Down in the corner, I know you can't really see it, but there's actually, on the x-axis, there's a graph. So if I start at 0, this graph goes horizontal up to 1, all the way over, way down to -2, over, back up to the x-axis. So that portion of your graph, after that spot, it would be a repeat. So the period of this function is 2 pi. And part D, to do the period here, we start at 0 and we loop to 6. We'd loop again. So the period then is 6. So the period is your horizontal distance. Now for sine and cosine, that's 360 degrees unless you actually change it. So somebody might make the period 180 degrees, which squishes in the graph, or maybe they stretch it and make it 720 degrees. Amplitude measures the distance between the maximum and minimum values on a periodic function. So the amplitude is actually this formula, but these graphs are pretty simple today. So everything's centered around the x-axis. So when you're centered around the x-axis, you really don't have to use the formula a whole lot, because when you're centered around the x-axis, your midline is 0. And so if you look at the first example here for part A maxes out at 2, and it minimums at -2, and so the amplitude would be 2. If I use the formula, I would take the maximum, subtract the minimum, which means add 2, and so you're going to get the absolute value of 4 divided by 2, which is 2. Just by looking at it, though, if the middle line is 0, you don't really have to calculate that a whole lot. So I'm not looking for 4. I'm not looking for the distance between the max and the min. I'm looking for half that distance. If you look at part B, it tops out at 8, it bottoms out at -8, so my amplitude is 8. In part C, I'm topping out at 0.75, I'm bottoming out at -0.75. Amplitude has to be positive. It's a measurement, it's a distance. So now amplitude is actually the vertical distance of the graph. And the amplitude of sine and cosine was 1. Because it went up 1 and it went down 1, the amplitude would be 1 of the parent function. But again, we can stretch that and make it go up to 2, or we can condense that and compress it and make it only go up to a half or a quarter. So just to practice amplitude, we're going to practice a couple different things here actually. We're going to bring it all together. We're going to determine if it's sine or cosine based on whether it peaks and valleys, or if it starts, if it's a peak or a valley. We're going to determine the period and the amplitude of each. So these are all different sine and cosine curves that they messed with. So if you look at A is going to be a sine function, because if you look at 0, it starts at 0. It didn't start up, it started at 0. So that is the easiest way to determine whether it's sine or cosine. So this is a sine function. Okay, and then now I look for the repeat. So I'm looking for a peak and a valley, and it peaked and valley at 180 degrees. So the period here is 180 degrees. So they actually compressed the parent function. And then its amplitude, it goes up to 4, and it goes back down to -4, so the amplitude is 4. Now you don't have to draw this, but I just want to show you what the parent function actually looks like here. The parent, if this was the real parent, it would go up to 1, back down through 0, down to 1, and back up at 0. So you can see how they stretched it vertically, and then they squished it in, compressed it horizontally, so that we can actually see 2 repeats within the 360 degrees. Part B. Okay, this is a cosine curve. It's cosine because it starts up at 0. So 0 is up. So that's my clue that it's cosine. And then when I look at my valley and my next peak ends, I know they didn't show it, but it's at 360. So they didn't change the period here. The period is 360 degrees. So it was not stretched or compressed horizontally, but the amplitude changed quite a bit. They actually stretched it 5 units. So again, I can try to sketch really quick what the parent function would look like, and that would look something along these lines. They just really stretched it from where it was. Maybe like that. Part C. Part C, looking at it, it's a sine curve because it's starting at the origin. And the period here, when I peak and valley at 90 degrees. So you're actually going to see 4 repeats, 4 peaks and valleys within 360 degrees because they condensed, they compressed horizontally. And the amplitude stayed the same. It was just 1. So the parent function in this case would look something along the lines of, it didn't really go any lower or higher, they really squished it in sideways. And part D is a sine function because it does start at 0, 0. When it peaks and valleys, the period stayed 360 degrees. And the amplitude, though, we top out at 3 and at -3, so they stretched it vertically 3 units. Okay, so that's everything in a nutshell. Now we're going to actually take a description and do a sketch. So for number 4, we're going to graph a cosine curve. We're going to keep in mind we need 5 basic points. The period is 180 and the amplitude is 2. So here's my rule as far as sketches. Since the period is less than the 360, I want to see all 360 degrees, at least 360 degrees. If your period is greater than 360, I just need to see to that period. So you're going to see a couple repeats here because it was shorter. We condensed it. We compressed it. So the cosine curve, remember I told you that for cosine, we need a beginning point, and it actually starts up top, right? So it begins at 0, and then it would end at 180, not 360 this time. Because of symmetry, we know that halfway is 90 degrees, and at 90 degrees, it'll be down low. And then the other halfways, I don't even need to label those. As long as I have the beginning, the end, and the middle, I'm good. Now, I can actually label those as 45 and 135 just because I know that half of 90 is 45. So this is just done on your calculator. Divide by 2, and then divide by 2 again. You're cutting it into fourths. You got your first fourth between 0 and 45, then between 45 and 90, between 90 and 135, and between 180. So you cut the graph into 4 parts with these 5 points. So make use of your paper. You're going to make your coordinate plane long all the way across your paper. And my amplitude is 2. So you can use the lines of your paper. You can go up 1 space. You can go up 2 spaces. I really don't care. Just make sure you label them and you're consistent, whatever scale you use. And then all I need is that I want to see 360. So I'm actually going to start in the middle as 180. And then mark 90, and I'm just eyeballing these, just cutting it in half, and then half again. Now I think if you had the pre-printed, you had these increments in there, and I apologize. It's really actually easier to increment as you go. And then I'm going to put 360 at the very end, because that's going to be my second round, because I can fit another valley in here as I go through. So halfway between 180 and 360 is 270. That makes us 225, and that makes us 315. You just add 45 each time. All right, we're going to make our guidelines at 2 and at -2. That just helps guide us to keep us straight. And then we're going to do our 5 points. So for our 5 points, cosine starts up. So we're going to start at 0, 2. That's my ordered pair. I'm going to end this first period up at 182. We'll deal with the second period in a second. We're going to finish this whole period. If I'm up at 180, halfway would be 90, -2. So I'm going to be down. And then middle. So 45, 0, and 135, 0. And I can go ahead and make my first valley. Okay, I always try to cup it in the beginning because it kind of shows that next peak. All right, then we repeat the process. I'm up at 180, which is now my beginning. I'm up at 360 and 2. The middle would be 270, -2. And then we'd be at 225, 0, and 315, 0. And we just connect. And there you have your 2 valleys because we squished it in. The parent function, you don't have to draw this, but I like to show you where the parent function would look. The parent function would start here. It would end here. It would be down here. And it would go through at 90 and 270. And so the parent function, you can see that they stretched it both vertically and then they compressed it horizontally. All right. Next example is the sine curve. Now the period is stretched horizontally 720 degrees. So I only need to see one of these complete periods because it's bigger than 360. And it has an amplitude of a half, so they compressed it vertically. So again, draw a line all the way the length of your paper. You can use one space. I would really not encourage using a half of a space. It's just too squished. So use one or two spaces. I really don't care. The most important part is labeling it a half and negative a half. And then I'm going to just do some pre-planning off to the side, 5 points. I'm going to start at 0. I'm going to end at 720. That means my middle point will be at 360. The middle of my middle will be at 180. And the middle of the middle, where my valley is 540. There we go. So I'm going to label at the very end, 720. I'm going to eyeball halfway, call it 360. Eyeball halfway again, 180. And eyeball halfway again at 540. Keep doing the 270 there. That is 540. And then we get our 5 points for our sine curve. I do want to make my guidelines going from a half and a negative half. So it's going to be one great big peak and one great big valley. So I'm going to start at 0, 0. I'm going to end at 720, 0. And I'm going to hit the middle at 360, 0. I'm going to peak at 180, a half. And I'm going to valley at 540, negative a half. This is one great big stretched period, but compressed amplitude. And just to show you what the actual parent would look like is something along the lines. Oh, I lied. I went too far. Let's try that again. We're going to peak up here. I'm going to go through 180, and then we go down below and end at 360. All right. Lesson summary. My advanced algebra kids just ignore this part, but this is for my algebra 2s. What is the period of a sine curve? And then give the period and amplitude of the given graph. Good luck.